So we've already discussed polar coordinates. This is the two-dimensional circular type of geometry. A circle is a cross-section of a cylinder. So if you wanted to extend polar coordinates to the third dimension, it would be called cylindrical coordinates. So here I've shown you a graphical representation of cylindrical coordinates. This is the position vector. It's not that straight, but it's the position vector pointing to this point here. Then we can identify this, the x, y, z coordinate of that point using three different variables. Here it would be rho, which is the length. If you project that point onto the xy plane, it's the length from the origin to the projection on the xy plane. And then the angle that projection makes with the x-axis is phi. In polar coordinates, we call that this r and theta because that's kind of the standard in 2 dimensions. When we go to 3 dimensions now, we're calling this rho and phi. And then the third coordinate is z, the vertical height above the xy plane. Okay? And that specifies this coordinate. So this is just polar coordinates. Instead of r theta, we use rho phi. Polar coordinates expanded into the third direction. The position vector then is written as rho times rho hat. So rho hat is the unit vector in the direction of rho, plus z times z hat. Z hat was our k in Cartesian coordinates. And the third unit vector then is phi hat, which is in the direction of increasing phi. So the change of variables formula from Cartesian coordinates to cylindrical coordinates is x equals rho cosine phi, y equals rho sine phi, and z still is the Cartesian coordinate z. You can compute the Jacobian here to get the change of the dx dy volume element, a change of variables formula. And if you do that as part of your problems, you get dx dy dz. Well, it's actually, we did it already for polar coordinates. It would just be rho, d phi, dz, because the z coordinate doesn't add anything to this. Okay. We need the differential operators in cylindrical coordinates. It's a lot of work. It requires doing a chain rule multiple times. So let me just write down the formulas and explain to you what they are. Okay, so the del operator in cylindrical coordinates is 3 terms, rho hat dd rho, plus phi hat 1 over rho dd phi, plus z hat ddz. So there's this extra factor of 1 over rho. Remember that both rho hat and phi hat are functions of phi. So when you differentiate, you always have to make sure you differentiate the unit vectors. Okay, let's look at the Laplacian now. Okay, so this is the Laplacian operator, a bit more complicated. 1 over rho dd rho of rho dd rho. So this has both a first derivative in it and a second derivative in it, plus 1 over rho squared d phi squared, and then plus d squared dz squared, because the z unit vector is fixed, doesn't depend on phi. So if you wanted to solve a PDE that has some sort of cylindrical geometry associated with it, such as the electromagnetic field inside a cylinder cavity, then you would need this form of the Laplacian. Okay, Now let's look at what do you do if you have a vector. So our vector A, say, has components in the rho direction, the phi direction, and the z direction. So I'll write that as A rho times rho hat plus A phi times phi hat plus A z times z hat. So A rho is a function of rho, phi, and z. A phi is a function of rho, phi, and z. And AZ is a function of rho, phi, and z. So now I want to talk about what is the divergence of A in cylindrical coordinates and what is the curl of A in cylindrical coordinates. So let's have a look at that. Okay, so this is the divergence of A, and this is the curl of A. You see how the expressions are quickly becoming complicated. So the divergence of A is 1 over rho d rho, rho times the component of A along the rho hat direction, A rho, plus 1 over rho dA phi d phi, plus dAz dz. Okay. The curl is more complicated. So the del cross A, the component in the rho hat direction, is 1 over rho dAz d phi minus dA phi dz, plus the component in the phi hat direction is dA rho dz minus dAz d rho, plus the component in the z hat direction is 1 over rho d rho rho a phi minus 1 over rho dA rho d phi. Okay? Quite complicated. So I'm capable of deriving these things, but I wouldn't want to. They're very messy. They're in the textbooks. When you need them, when you're solving a problem that has a curl of a vector field or a divergence of a vector field in the problem, and the geometry of the problem corresponds to cylinders, then you pull out your textbook and you look up these formulas. Okay? Same for the Laplacian and the gradient operator. Okay, this is cylindrical coordinates. Next up will be spherical coordinates. I'm Jeff Chasnov. See you in the next video.